All right, do you like really tedious problems? I hope so, because that's what this is. So let's get right into it. So we got to prove that M and I is an ideal of M and R. So let's see, I did this on a homework assignment once, so I'm literally just going to copy this. So let A be a matrix, and B also a matrix, these both in M and I. Then for all I and j, aij and bij are in I by definition. So aij plus bij is in I. So A plus B is just the matrix aij plus bij, which is in M and I. Let A, let A be the same thing as before, and let R equal Rij simply be in M and R. Then if the matrix C given by Cij is AR, then Cij is the sum from k equals 1 to n of AIKRKJ, and that's just by definition. Let's see here. So see here, since I is an ideal, Cij is in I. And that's because, like, I'm not going to write out all the details like I did in the assignment, but AIK times RKJ. AIK is in an ideal, so you multiply it by RKJ and you get an element that's in the ideal. Then you add a bunch of these up, and you're adding a bunch of elements in an ideal, and so it's closed, and so you'll get an element of the ideal, and so Cij is an I. Okay? And let's see here, so C is in M and I. And then likewise, RA is in M and I. And that's just because if you do the multiplication, it'll be sum from k equals 1 to n of RIKAKJ, and that's going to be an element of the ideal for the same reason. So hence, M and I is an ideal in M and R. Okay, that wasn't quite as bad as I was expecting, partially because I went really quick. Prove that every ideal has this form. This is a little more tedious. So let I be an ideal of M and R. Let J be all the elements R such that there exists see here, Aij equals R for some entry Aij in A, which is a matrix in M and R. No, in M and I? No, in I. I claim J is an ideal and M and J equals I. So I is just any ideal. We won't prove that every ideal has this form. No, we want has the form M and I for some I in R. So we want let J be an ideal. I mean, the names don't really matter, but just to make it easier for you guys, we're going to let I be this for some entry A and J. I claim that I is an ideal and M and I is equal to J. Okay, so to prove I is an ideal, observe 0 is in, God, I'm gonna here, I have to take a second. So I used script alpha and script beta for the ideals in my homework, so I need to convert these for myself. So script A is just the ideal that we start with in M and I. So script A is going to be J, and script B then is going to be I. Okay, cool. This will allow me to copy this faster. Observe that 0 is in J because it's an ideal. So let's see here. So 0 is in I because the 0 matrix has 0 as an entry. Duh. Now let A and B be two elements of J. Then there exists an A in J. No, A and B are in I. So then there's an A and J and indices K and L such that the KL entry of A is equal to just A. Let EIJ be the matrix delta IJ, which has entry 1, the ring element 1, at the IJ entry and zeros everywhere else. Then obviously EIJ is in M and R. Let's see here. Also, EPQ times the matrix AIJ what is the matrix that is 0 except for the pth row, which contains elements Q1 through Qn. That does not sound right to me. Because EPQ hold on. It's your PQ and then AIJ. So when we're going through this, oh no, that's right. So EPQ times IJ is the matrix which is 0 except in the pth row where it contains AQ1 through AQN. You can just verify that. Then where am I going with this? Where is past me going with this? This times ERS has, so this is just delta. It's going to be a 0 matrix most places. What's going to have its PS entry will be AQR. Okay. So E1K AEL1 is in J. and has 1 entry AKL, which remembers A. By similar methods, there exists some B. Why do I call this B prime? No, okay. We're going to call E1K, the matrix E1K A EKL equals A prime. By similar methods, there exists a B prime in J whose 1 entry is B. Then A prime plus B prime is in J. And why are they in J? Because they're in J because A and B are in J, and we're just multiplying them by elements in M and R. And so these two elements are in J individually, and then J is an ideal, so you add them there in J. So these are in J, and it has 1 entry A plus B, so A plus B is in I. Good Lord, that was a lot of work for a very simple concept. Next, for all R and R, A prime R E11 is in J and has 1 entry AR, so AR is in I. Likewise, RA is in I. You can prove that yourself. I don't want to have to do it. And hence, I is an ideal. All right, so we're done, right? Nope, we've done half of this part of the problem. So, see here. I now claim that we have to verify that Mn of I equals J. If A is Aij is in J, then Aij is in I for all indices I and J, so A is in Mni, so then J, come on computer, I know I'm putting you through a lot. So J is a subset of Mni. Now let B, call it Bij, be in Mni. We want to prove it's in J. Then, given any indices I and J, there exists a matrix A, Aij, in J, and indices K and L, thank God my computer calm down there, such that Bij equals AKL. And why is that? No! Yes, okay. Okay, so if we're an M and I, then each Bij is an element of I. And so we can find some matrix in J who has that as an I, as its element. Okay, so define A equals I don't know what I wrote here. I said to write A to be equal to Aij. Oh. Right, because fixing any indices I and j, I should really write this. There exists an Aij, which is just A, and then we'll say, instead of using Ij indices here, we're going to use R and S. And this is in J, and so Bij equals AKL. So actually no. We have to do more than this. So we're gonna erase a bunch of stuff once my computer can do it. Okay, so A is ARS. I'm just going to leave the RS. So now we're going to write, so A depends on Aij, and then K and L from the last sentence also depend on Ij. So let's see here. So then the matrix Bij equals, we can write B as being the sum over all indices of E, I, K, I, J, A, I, J, E, L, I, J, J. Here, I'm going to put commas in here. That's not a sigma, that's an E. So E of I, comma, K, I, J, A sub I, E of L, I, J, comma, J. You can verify that. I didn't lose any points on this, so I guess that means that this is 100% accurate and there's no better way of doing this. No, there's definitely got to be a better way of doing this. Or maybe not. I don't know. This might be algebra and they were just like, oh, let's just do a whole bunch of tedious things that are really easy, and then in like a few pages we'll get to something that's like ridiculously hard, and it's only easy if you know how to do the exact right trick. Anyways, since J is an ideal, each Bij is in J. What? A is an ideal of M and R, so it doesn't make sense for this product to be an element of J. Oh wait, yeah, it does. Because, oh yeah, this is just matrix multiplication. So it's not that each Bij is in A, it's each EI, KIJ, AIJ, ELIJ, each of these is in J. And so B is in J. Because it's just a sum of, oh god. Okay. So B is in J. Alright. So thus, MNB for Mni is contained in J, so Mni equals J as desired. All right, now this completes the proof. Ha, just kidding, LOL. We're not done yet. We gotta prove that we have a relation between the ideals of R and the ideals of M and R, and given by a bijective map. So finally, if I and J are distinct ideals in R, then M and I and M and J are distinct ideals in M and R. They're ideals because we just proved that ideals are of this form, and they're distinct because if I and J are distinct, then you can just come up with matrices that just consist of elements that are different from the two, and so the ideals cannot be the same. Since every ideal is of the form M and I for some ideal I of R, the map is surjective, and hence the map that sends an ideal I of R to the ideal M and I of M and R is a bijection. Thank God. Okay, now we've finally completed the proof.